All right, today we are diving into something really strange from the world of computer science. We're going to look at a place where adding just one tiny, almost harmless-looking feature to a system of logic, well, it makes it almost impossibly complex. It's kind of like a journey to the very edge of what's computable.
So, let me ask you this. What if you had a system that was totally manageable, completely predictable, and then, bam, it becomes almost impossible to figure out? And the only thing you changed, you just gave it the ability to remember one single piece of information. It sounds completely backwards, like a paradox, right? But believe it or not, it's a real thing, and we're going to unpack it right now.
Okay, so let's just dive right in. We're about to uncover a type of problem that is so ridiculously difficult, it actually makes us question what we even mean when we say a problem is hard.
And the name for this level of difficulty is non-primitive recursive. Yeah, I know, it's a total mouthful, but don't worry about the jargon. All you really need to grasp for now is that this isn't just hard or very, very hard. No, this is a completely different kind of beast. We're talking about problems that grow in difficulty so incredibly fast that they just leave our usual ways of measuring complexity in the dust.
And just to put that into perspective for you, think about some of the most famously difficult problems in computer science. Even those are still considered solvable, within known limits, even if those limits are massive. But non-primitive recursive problems? They're on another planet entirely. Yeah, they're technically solvable, but the sheer amount of resources you'd need is, well, it's just mind-bending. So our goal today is to figure out what incredibly simple-sounding rule is capable of creating such a monster.
Okay, to make this idea a little more real and less abstract, let's step away from the pure logic for a second. Let's go on a little road trip. I like to call this the one-memory GPS analogy.
So first, just imagine a totally normal journey. You're driving down this road that just goes on forever, and your only job is to look at the signs as you go by. Pretty simple, right? You can check if you see a specific sign, or maybe if one sign shows up after another one. This is basically how standard computer logic works. It's predictable, it's manageable, no surprises.
But now, let's add one tiny little upgrade to your GPS. It gets a single memory slot and a save button. That's it. Now, at any point on your drive, you can hit that button and freeze your exact coordinates. Just one set of coordinates. And your new mission, your only goal, is to figure out if you will ever, sometime in the infinite future of this road, end up at a location with the exact same coordinates you saved. And that one simple task, that's where all this crazy complexity comes from.
All right, so with that GPS road trip fresh in our minds, it's time to meet the actual culprit behind this complexity cliff. It has a formal name, and I'll admit it looks a little intimidating at first. There it is, LTL with a little down arrow, subscript 1, F. It looks complicated, I get it, but the cool thing is, thanks to our analogy, you actually already know what every single piece of this means. So let's just break it down together.
First up, LTL. That stands for Linear Temporal Logic. And in our analogy, that's just the infinite road itself. It's the way we talk about things happening one after another in a sequence over time. Next, that little down arrow, that's called the freeze quantifier, and that is our magic save button. It's the action of actually storing your current coordinates, saving them in that memory slot for later.
Then you've got the little subscript 1, and this is absolutely crucial. It means we have only one register, just one memory slot in our GPS. That's the key constraint that makes this whole thing so interesting. And finally, that F in parentheses. That's the eventually operator. This is what frames our whole mission. We're not asking if the matching coordinate is the very next one we'll see. We're asking if we'll find it any time in the future. Will we eventually see it again?
So, when you put all those pieces together, what you have is a logic that describes an infinite journey where we can save one single location's data and ask if we'll ever see that exact same data again. Simple enough, right? Well, now let's actually look at the consequences of these simple rules. Let's see what life is really like on the complexity cliff.
I mean, look at this. The sheer scale of the jump here is what is so shocking. On the left, you have your standard LTL. It's PS space complete, which is a fancy way of saying it's hard, for sure, but it's solvable with a more or less predictable amount of computer power. But then on the right, you add that one little freeze register, and the complexity just explodes. It becomes non-primitive recursive. We've literally gone from climbing a steep but totally climbable hill to staring up at an infinitely high cliff.
And this logic, it's so extreme
that it basically lives right on the razor's edge of what is computationally possible. It's what we call decidable, meaning that, in theory, an answer does exist. But it is so precariously close to that edge that just the tiniest little nudge can push it right over into the realm of the undecidable. And that's where you find problems for which no algorithm could ever guarantee you'd get a correct yes or no answer.
And this table here, it just illustrates that tipping point perfectly. Look at the top line. That's our logic, the one we've been talking about. It's decidable, even though it's insanely hard. But now look at the second row. You just add the ability to look backwards in time, boom, undecidable. Or check out the third row. Add a second memory slot. Just one more little register. Again, it tips right over the edge. It is just balanced on a knife's edge.
So this really brings us to the big question, the core takeaway here. Why? Why does this one single tiny feature have such a massive, monumental impact on how complex everything gets?
You know, the researchers who first figured this out, they really summarized it perfectly. The whole thing boils down to this. It's the ability to specify that some distant future state must exactly match that single saved coordinate. That link, that connection across a potentially infinite amount of time, that's what makes trying to reason about the system so unbelievably difficult.
And look, this isn't just some abstract puzzle for computer scientists. This really matters in the real world. Think about it. When we're designing incredibly complex software, for things like airplanes or banking systems, we have to be able to prove that they work correctly. And the discovery of logics like this one shows us that a feature that seems totally innocent, like just storing a value to check against later, can create a monumental, almost impossible challenge when you're trying to prove that a system is actually safe and predictable.
And that really leaves us with one final thought to chew on. If just a single memory slot can create this much hidden explosive complexity inside a formal system of logic, it makes you wonder, right? What tiny, seemingly harmless features in the technology and the software that we all use every single day might be hiding their own complexity cliffs, just waiting for us to stumble upon them?